Yeah, thanks for the introduction, and I'm very glad to be here sharing about my research in the partition functions. And actually, this thing is the main part of my PhD thesis. I've just graduated. So from the title, is it hearing well for my voice?
Yeah, it's very good.
Okay, yeah. And from the title, we can see that there are three parts of them, and I need to clarify each part of them. The first is how we say about our partition functions, and then why we define the rank of it, and then why it is important for the exact formula of them. And here is about the contents. First, I will introduce about the partition function itself. And we can see a little bit pattern about how people come from the asymptotic formula and goes to the exact formula. And you will see the pattern again and again for the examples for the rank modulo 2 and 3 in the second part. And the main the main result of this presentation is for the part 3, where I introduce about my proof of the exact formula for the prime larger than or equal to 5. And after we have that for the prime equal to 5 and 7 cases, where these are the cases for the Ramanujan's congruences, we will see a new proof of the Ramanujan congruences. Well, I know there are many of proofs here, but I'm pretty sure this will be a very crazy one. Okay, let me first begin to introduce about the notations, about some basic things about in the slides. A partition of n is the way we write positive integer as sum of positive integers. And we require everything to be positive, and we write it in the decreasing way to make sure we don't have any repetitions. There's sum to be n, and Pn is number of ways we write all the partitions, the number of ways to write all the partition of n. And for simplicity, we just write P0 to be 1. For example, we have P4 is 5, which means we have the following 5 ways to write 4 as sum of positive integers. This function, this arithmetic function or partition function, has a generating function looks like this. In the beginning, we have this one, and as usual, we have absolute value of q to be less than 1. And it has the infinite product case, and it has also the last case, which is also known as some Euler's formula. But you see the q to the power n squared in the numerator, which looks very like a theta function. So it's in some sense divided by this one. And what I know about the proof here is you can do this from some combinatorial way, the Dirichlet squares. But in this slide, we are focusing more on the analytic side of the functions. The first result by the partition function for the partition function is by Harding and Ramanujan in 1990, where you can see the growth of the partition function itself is about exponential of square root n, which is not as fast as exponential, not as slow as the polynomial. But the result by Harding and Ramanujan is not that simple. They actually got a symptotic formula up to several terms up to square root n, where they first define exponential sum like this. This is a canonical symbol, and this is our exponential e to the 2 pi iz here. And you will see a Dedekind sum appears here, and not just exponential itself. The result by Harding and Ramanujan is actually we can summing up from c equals to 1 to a level of square root n, and this the first few terms play like n. And the others, if we look back to the first term here, this one is just the first term in that finite sum. We were just dividing pi over 1 for the first term, pi over 2 for the second term, and dividing pi over c for the cth term. And there's a reason why we're summing up to square root n, because when you're dividing square root n here, everything here will behave like a constant. And we may not have very good estimation about the terms after that. But this formula converges very fast compared to Pn itself. Like for example, if you take n is 200, then the first term is very near to the Pn itself, which is very large, and the second term is just 300, which is very small, and up to the fifth term, there will be less than 1. And people have a very strong hope that this summation, this asymptotics, when summing up to infinity, should equal to Pn itself. And this is a result by Rademacher in 1938. That's summing up to infinity. This will just equal to Pn. That's why we call it Rademacher's exact formula. And you can see a Dedekind sum as a special sum S of dc appears in the exponential part in the exponential sum here. And the reason for it appears there is we define the Dedekind eta function like this. And you can see the infinite product here. So if you write n to the power of q to the power of -1 over 24 on the left-hand side, which I really like in this way, you see the reciprocal of 1 over 8 and the transformation law of eta function. The most important part gives the Dedekind sum here. And this one is just constant, and this part is as the compensation of this 1 over 24. So it doesn't matter. As the key reason is it appears as a modular form here. After we have seen the pattern for the partition function itself, we know the first term is asymptotics. We know up to square root n terms of the asymptotics, and then we prove the convergence for the exact formula. Let's see a few of more examples, modulo 2 and 3 cases, where we will introduce a new notion of rank, Dyson's rank. Dyson's rank originally comes from Dyson's interpretation of Ramanujan's congruences. The first line is the famous Ramanujan congruences, where you can see 5n plus 4, 7 plus 5, and 11 plus 6. In those three cases, Dyson gives us a new interpretation of the first two of them, which it defines the rank of every partition to be the biggest part minus the number of parts, and it count the number of partitions of n with special ranks, which rank equal to m or rank equivalent to a mod b. Those counting functions interpret those congruences in this way. They classify all the partitions of 5n plus 4 into 5 same sets, and everything is accounting, so this one is just multiple of 5. And also the reason for 7. This was originally proved in 1950s by Atkin and Swinton Dyer, and Dyson believed that there should be another interpretation for 11, and actually this is found by George Andrews in late 1960s. Now we are focusing on the rank counting functions here. It also has a generating function, but now we have two variables. So we introduce a new variable in the inner sum with the root of unity here, and also the outer sum is just q itself. And I want to mention that inner sum here is a finite sum. It goes because every rank can be at least 1 minus n and at most n minus 1. So it's a finite sum here, so it will not cause some convergence issues here. And we call the inner sum as the Fourier coefficient of the rank generating function. Let's see for a few examples about the values if we take the root of unity as different things. First, if we take u is 1, so the inner sum, we are just sum up every partition of n with different ranks. So the generating function will be Pn itself, for the generating function of Pn itself. And we already have Rademacher's exact formula, which I rewrite it in this way. We use the Kloosterman sum notation with eta multiplier here and Ibison functions. This is the same as before, but to make everything to be uniform, for the notation to be uniform, I prefer this way to write it here. And if we take u is 2, then this will be just -1 to some power of m. So we are actually just summing up all the even ranks minus number of odd ranks. And the generating function now becomes Ramanujan's third order mock theta function. Where when Ramanujan was alive, he also gives a conjecture about the Fourier coefficient of his mock theta function. It is actually the first term asymptotics, which looks like Harding Ramanujan 1919 for the partition function itself. And that conjecture for the first term asymptotics was proved by Dragonet in 1950s. And Dragonet also writes as a few terms up to square root n. We have seen the pattern before, which was the error term was estimated better by George Andrews in 1960s. And the exact formula is not proved until 2006 by Brinkman and Ono that we can see now it's a sum up, we can sum up to infinity, not just to square root n with some error term. And so this is the second case of the exact formula. And for the third case, if we take the third rule of unity, then the rank generating function becomes again a sixth order mock theta function. And its Fourier coefficient has asymptotics was proved by Brinkman in 2009, that we can see this pattern again. We sum up to square root n and with the error term n to the positive power of epsilon. So we don't know in this time 2009, we don't know if this converges, but we have a very strong hope that it should converge back to this quantity. The method by Brinkman and Ono, they proved this as the exact formula. It's quite new. It's quite different from the method people proved the symptotics before. Previously, people used circle methods to prove the symptotics, but by Brinkman and Ono, they used the theory in harmonic mass forms where, let me introduce a little bit about the notations here. We begin with a hyperbolic collapsion defined as this, and we fix k to be half integral. Actually, k can be integral, but because of our notations of the theta multiplier here, I prefer it to be, and every case here we are talking about is V1/2. So just use this notation. We have congruence group gamma 0 n, and it has the modular transformation property, and its eigenvalue under the hyperbolic compression has to be 0. The third part is most important. We have every harmonic mass form should have some principal part, which we call the polynomial. Should have a polynomial, which we call the principal part. It is a negative. It is a polynomial of q to the power of -1, and their difference should be controlled on different on every cusp. And this is we call the principal part because it means that it shows the principal part of the harmonic mass form at different cusps. And we use HK to notify the space of those functions. Here are some examples of harmonic mass forms. For example, the first one is we must be more familiar with this. Those are homomorphic theta functions. These functions don't have, or I should say, they have constant principal part on all the cusps. And another good thing is we have Sears-Stark's basis theorem, which says they generates the basis of V1/2 modular forms. We're just focusing on V1/2. And the way by Brinkman and Ono they prove that is to construct the mass Poincare series like this. They use the special function phi. I will show it later. And this Poincare series match the rank generating function we have seen before with its non-homomorphic part. And for Poincare series, we know that we can calculate its Fourier coefficient in some classical way. And its Fourier coefficient will be written as sum of Klussmann sums. And that's why we can show that sum of Klussmann sums will equal to the Fourier coefficient we have seen before. And this time, if we are, even we haven't talked about the p larger than or equal to 5 cases till now, but I would like to show that we will define Poincare series on different cusps. This A here marks the cusp of any congruence group gamma. And here, this is only for the cusp infinity for the previous case. And I want to show that the principal part is quite important in the theory. And this was, the first result comes from 2004 by the paper by Brini and Funk. And it was later used by Brinkman and Ono in their paper to show in the proof. So for harmonic mass form, it can only be two cases. Either only have the homomorphic part, or it has the principal part and the non-homomorphic part. And because the principal part is just a polynomial of q to the power of -1, it's finite polynomial, it means if we decide the principal part of a harmonic mass form, then we know everything about the harmonic mass form. And one good thing about the Poincare series is that every Poincare series we define only has principal part at the special cusp, at its definition, and it don't have principal part at the other cusps. So which means if we know the principal part of harmonic mass form, we want to match it well, then we can construct different Poincare series to match every principal part, and the linear combination of them will show us show that they equal. And if we show them equal, we can calculate the Fourier coefficient of Poincare series, which looks like this way. This is on the right-hand side for the Rademacher type of exact formula we want to prove. And on the left-hand side is the Fourier coefficient of the rank generating functions. And actually, this is the whole idea of every pattern we have seen here. Okay, so the proof idea is, the proof idea is here for proof of something. Maybe for the model 3 case is just listed like this. We find the correct group, a congruence group. We find the correct multiplier system. We construct special Poincare series to match the principal parts at different parts. And we compute the Fourier expansion of those Poincare series, which is classical. And the only thing matters is for its convergence. We will talk about later, because in definition of those Poincare series, they're convergent when the real part of S larger than 1. But we need S to be 3/4, which is less than 1. And that's some convergence issues here. And I want to say here about model 3 case, which was written in my previous paper. It's on gamma 03, and the principal part of this, not this one, it should be added with non-homomorphic part. The principal part of that harmonic mass form has constant at cusp 0. So we only need to match cusp infinity. And we know the multiplier system. We know the Fourier expansion. We can deal with some convergence with estimating some of Kuhlmann sums. And we have the same idea, which I want to show. What I actually want to tell here is we can prove model 3 case with the same method as before. And the convergence matters here. We use this seed phi function using the M-weighted functions. It's a special function. And we construct Poincare series using this. You have seen it before. But the Poincare series is convergent when the real part of S is larger than 1. But to make it harmonic, which means it has to be eigenvalue 0 under the hyperbolic Laplacian. But if we take any S, then this eigenvalue should be written as this. And if we have S is 1 minus k over 2, and in this case, k is 1/2, this eigenvalue should be 0. You can see everything equals and cancels. And we need some special convergent things on the Kuhlmann sum, which I just say it here. I didn't write it. I will not write it down in the slides. We write the expansion including S. We are just assuming S to be appeared there, and assuming S to be a real part larger than 1. And we find that when we just take S to be 3/4, the expansion will converge, which means the original Poincare series will also converge, will be analytically continued to S equals to 3/4 and also converge. And the estimation, we will show it in the very end, but just some important things matters here. And now let's come to the main proof, and the main theorem I proved here for the ranks of partitions, for the exact formula for rank generating functions when p larger than or equal to 5. The work did by Brinkman in 2009 is not just for modulo 3. She actually did that for all the odd number larger than or equal to 3. And you see a very complicated asymptotics here, which the first term, if you think this as a Kuhlmann sum, looks very like the patterns we have seen before. The error term I put it here. And the second term, I should say that this is a finite sum on R, which at that time, people don't know how it comes from. And this R is finite because when R is large enough for a fixed U, this delta is always negative. So it cannot have a double infinite sum here. And we are considering about to prove this formula to be convergent to that in the prime case. Why? Because there are a few reasons. Gamma 0p, we believe that the rank generating function should transform on gamma 0p. And gamma 0p only has 2 cusps, and which makes us to matching the Poincare series to be easier. And those very complicated exponential sums, complicated parameters m, delta, b, and d here, will be a little bit more simpler in the prime cases. And the last but the most important case is that we still don't know the multiplier system yet, but the transformation law is proved by Garba in 2019. And yeah, let's see how things works in our preparation. First, we define a few of the functions, g1, g2, this g1, this g2, a lot of them. But we only need to focus on g1 because g1 is the completed, like the rank generating function is its holomorphic part completed by its non-holomorphic part. And others, you can just ignore them. And there's one important theorem by Bremen and All in 2010 that everything together, this is about p squared terms of them, everything together will be a vector value mass form transforming on SL2Z. But we don't need all of them. We want to know only for this G1. And the special observation by Darwin in 2019 is that if we only focusing on G1, then if we take gamma on gamma 0p, then G1 transform back to G1, but to a different different G1. If you take L is anything coprime to P, well, from 1 to P minus 1, and it transforms to DL, which this bracket means we reduce DL to 0 to 2, from 0 to 2p, this notation. So G1 transform back to another G1, which means if we take G1 as a vector, if we run every G1 here at G1 of 1 over P, 2 over P, P minus 1 over P, if we take it as a vector, then this mu factor here and the eta multiplier will make it up to a matrix, and G1 will now behave like a vector valued something modular form with the multiplier system of this mu p. Not actually a multiplier system, now it's a multiplier matrix in front of it and have the good transformation properties of this mu. But how do we know anything about the vector valued multiplier systems? We can recall for the scalar value theory of the multiplier systems. Its absolute value has to be 1. When you transform on minus I, it has to be this one. And it has some compatibility requirements if we take product of two matrices. And so we have introduced the definition of the vector valued multiplier system in this way. The matrix has to be unitary, which means its inverse has to be its Hermitian. And also the same thing for minus I, also the same thing for the product of two matrices. And I require one thing more to make it this transformation law as diagonal matrix. I don't think this is very reasonable if we naturally just define a multiplier system in this way, but I want this property because I just want to write its Fourier expansion in different cusps, which means if it's diagonal, we can write its Fourier expansion at cusp A. And luckily, our defined mu p, the special transformation formula, matches every requirement here. So we have mu p defined before, and the parameter on cusp infinity is just 1 over 24. This is simple. The parameter on cusp on cusp 0 is decided in this way, which depending on L. And if you put L inside here, this should be e to the power of 1/2 L, or 1/2 plus 1 L, or like maybe 3/2 L, 5/2 L, any integer plus 1/2 L to be here. And why this is important? Because for the parameter here, we can see a similar pattern in Bremen's paper, which Bremen calculated completely from the circle method in a different way. So in Bremen's paper, these two complicated parameters is written like this. If you multiply by p for this one, you will see 3 halves here. You will see 1/2 plus r here because you can plus any integer if you put the minus 1 to the L here. And you can see 1 over 24 is p over 24 here. And this gives us a magic equation of this one. And we mark xr as the only solution on the left-hand side. And we mark this very funny notation of this r as the symmetry from 0 to xr and on the other side. Well, this just for notations. You'll see everything in the reason in the later slides. The thing we want to know is G1. And the thing we actually want to know is the behavior of G1 at cusp infinity and cusp 0. At cusp infinity, it's not hard. It's just n minus 1 over 24 because of the rank generating function itself. The behavior of G1 at cusp 0 is transformed by the scaling matrix, and is actually the behavior of G2 at cusp infinity. And for the expansion of G2 at cusp infinity, we can see something happens here. We can see this equation happen again. 3/2 x squared, 1/2 x, 1/24, and everything here, every term, if you multiply it in front of it, is 1/2 plus 1, 1/2 plus 0, 1/2 plus 1, 1/2 plus r, and this one has to be negative to make it the principal part. Remember, the principal part is the polynomial of q to the power of -1, so it has to be negative to be principal. And if this one is negative, you are adding L over P again, and it will end at some R such that it is positive, which recalls back the second sum in Brimmer's asymptotic formula that the summing on R is finite. So the order of G2 at cusp infinity, we define in this way with different R. So the range is decided on different on both sides. It's symmetric from 0 to xr and 1 minus xr to 1. And let me show why I use this funny notation of two triangles here by a graph. I draw it in decimals. So in this case, we fix for the prime 37 because 37 is the smallest prime such that r can be taken value as 0 and 1, not only 0, or not only we don't have any r here. For 37, you can see the equation here. For the first equation, the red line is r equal to 0, is the red line here. And every black straight line is 1 over p. So 1 over 37, 2 over 37, 3 over 37. And intersection points here, which is less than 0, the y value is less than 0, which is actually the correct order to be matched. The principal part, q to some power, q to this power, at cusp 0 of G1. And this is r equal to 0 case. And for r equal to 1 case, this is the blue line here, you can see only 1 over 37 intersects, and the other are all positive, and positive are not principal parts, only we need the negative ones. And for the green ones, r equal to 2 and more, they will become steeper and steeper. There is no more intersection anyway. So this means our summation of r in the second term will end in r equal to 1. And the triangle just because this thing looks like a triangle, like this one and this one. And it will be symmetric on the right-hand side. Okay, we have set up everything in our proof. And let's go back to the theories. We define Poincare series. This one, P infinity, is for cusp infinity. You can see that gamma infinity here is the stabilizer of cusp infinity. Its principal part at cusp infinity is this one to be matched for the principal part of G1 at cusp infinity. And we define Poincare series at cusp 0 in this way. A little bit more complicated, but everything is classically in theory. You have the you can find the theory in some books like by Ioannis. And we require this L to be fixed in that range because only in that range we will have our principal parts. We don't want the principal part on other cases. And still on cusp 0, and we calculate its principal part at cusp 0 to be matched. But it's only for fixed r because we have r is a new variable here. And after everything is set up, we have our vector G1 to be matched for its principal part to be matched. We have P infinity to match its cusp at infinity. We have P0 to match its principal part at cusp 0. And if we minus everything, its principal part should be constant, which means in the theory of harmonic mass forms, it's just it will just be a holomorphic modular form. Well, vector value thing is vector value because our mu p is a matrix. But if we take z to 24z, then we become scalar things. There's some good properties of mu p here. And the thing we want to prove is that g to be 0. We want this difference to be 0. And on the left-hand side, we have our Fourier coefficient to be matched. On the right-hand side, we have our sum of Boltzmann sums, which are the exact formulas. We can prove that g is 0 by some properties of mu p, because I have said V1/2 homomorphic modular forms, they have the basis of theta functions. And those theta functions should satisfy, I mean, the mu p when it goes z to 24z should satisfy the transformation formula of those theta functions, and you will find some contradiction there. Okay, yeah, this is well, we have got to the half step of the main theorems here. There are two last things we need to finish before we state our main theorem. One thing is about convergence. You have seen it before. The Poincare series are naturally convergent with real part of S larger than 1, but now we need S is 3/4. So we have to estimate those sums of vector value Kussmaul sums, not scalar value 1. But thanks to the result by Goldfield and Sarang in 1983, in that paper, they proved the symptotic formula for the sum of Kussmaul sums with very general multiplier systems, even any weight, and you can choose even weight in any real numbers. And now we have our special multiplier system. This is just one of the sum of Kussmaul sums we need to be estimated, but actually there are 6 of them. Just to show one example of that. And they have the main terms, they have some error terms like this. And the thing we want to prove is the following triple sum has to be absolutely convergent, where you need to take the absolute value very carefully, because this absolute value cannot be taken inside. We need some cancellations here. And if you take absolute value outer again, that thing is convergent. And this the thing happens for the Fourier coefficients in our calculation of Poincare series. And this convergence, which means the Poincare series can be analytically continued to the S equal to 3/4, which is also convergent and equal to this. Okay, we have Poincare series at cusp infinity, which gives us the Kussmaul sum at cusp infinity. Poincare series at cusp 0 gives us the Kussmaul sum at cusp 0. We have the convergence at 3/4. And because of the theorem we have proved before, they should equal. And now we have our main theorem. The Fourier coefficient, this is the Fourier coefficient of the rank generating functions, equal to the contribution from cusp infinity and contribution from cusp 0. If you remember a little bit about the asymptotic formula by Brinkman in 2009, you can see those formulas are very similar to each other. Also have the first term, the second term, summing up on R, but we use different notations. The second question is these two formulas equal to each other? I mean, every expression here should be the same as before. In Brinkman's formula, there's the sum here, the sum on R here, and we can prove that in a basic way, that notation in Brinkman is the same as the notation or as here. Even these things comes from 2 different sources. In Brinkman's paper, she did that from the circle method. In our paper, we did that from our multiplier system of G1, discovered by Garman. And after we have the exact formulas for ranks modulo P larger than or equal to 5, let's recall a little bit, think back. Why is the rank? Why Dyson comes for the rank? Because he wants to interpret Ramanujan's congruences. And now we have the exact formula for the rank of partitions. Can we say something again about Ramanujan congruences? Because this thing is for this n function, and our Fourier coefficients have this relationship with this n counting functions here. This gives an inverted matrix, which means if we know every value of A here, then we know every value of this n here. And equivalently, this equation is equivalent to every A here to be 0, which means this A, we take n to 5n plus 4, and this A is L over 5. And every L here, it should be 0. And this is just 0. And also the same thing happens for 7. We know Ramanujan congruences is true, so this too should be true. But this thing, in our theorem, it is the sum of Kussmaul sums. So this should be, you are summing infinitely many things which converge to 0, which seems very impossible. But the case here is every single term you are summing to, every single Kussmaul sum you are summing with, it's just 0. So you are just summing infinitely zeros. to 0, not convergent to 0. And the thing we prove this is by notifying a little bit about this thing has to be true for all n. And we want to prove it by induction. What happens if n goes to n plus 1? If it is true for n equals to 0, it should also true for n equal to 1, and this is our starting point. If we take n to n plus 1, in the expression of Kuhl's sum here, only this term will be affected because the other term doesn't include n. And if you take n to n plus 1 here, there's one more exponential term, 5d over c appears here, which means if we classify all the d up to c over 5, then this d will not be changed. So we introduce our new notation of VRC to cut all of d coprime to c. And depending on if c divisible by 25 or if c is only divisible by 5, we have VRC, we have number of points will be 4 or 5 here. And the summation on this VRC of these complicated terms should be cancelled to 0, non-trivially. In a non-trivial way, they are not just by some conjugation things. Let me show you some pictures, which looks like some funny pictures here. This is for the mod 5 case, where we have 4 points. And these 4 points cancels. If you sum up these 4 points on the complex plane, this cancels to 0. And for the 5 cases, for the VRC is 5 cases, they are just equally distributed on one circle, and that's not this hard case. And for prime equal to 7 case, there's 2 cases. In one case, we have 6 points on the complex plane, and they sum to 0. And on the other case, remember for the P prime is 7 case, we have 2 sums. One from contribution from cusp infinity, the other contribution from cusp 0. And for cusp infinity, those 6 points don't sum to 0, but it cancels with another term from Postman sum from cusp 0, this point here. And those 7 points cancels to 0. Well, these are just funny pictures. These are not theorems. Our theorems will read as this. So for prime is 5 or 7. For the first case, prime is 5. Every single Kuhl's sum is 0, which proves that since our exact formula is true, we prove that every a there is 0, so we give the reproof of Ramanujan congruences. In the second case, prime is 7. There's 2 cases. In the first case, every single term is 0. In the second case, this cancels with the Kuhl's sum from 0, and this to be 0. And every a here to be 0, we will give the reproof of that. Okay, and however, Dyson's conjecture is not only about Ramanujan congruences. There are a lot more Dyson's conjectures in different cases, not only for 5n plus 4, not only for 7 plus 5, but for 5n plus 1 and 2, and 7 plus everything else. And we have the exact formula. We know that those exact formulas for A are equivalent to some kind of exact formulas for those n. And can we prove Dyson's conjectures, every Dyson's conjectures, using the same method, some weird cancellation of those points in Kuhl's sums? The answer is yes. Actually, I've included in my paper about that proof. We can prove every term of Dyson's conjectures using my exact formula. And I think it's cool. Okay. Thank you for listening. And these are actually decided to 2 papers. In one paper, I proved the exact formula. In the second paper, let's show that those Kuhl's sums are equal to 0 in some weird way.
Okay, thank you very much for the very nice talk. Let's thank Qihang.